In the second part of Lesson 5, we're still going to continue our focus discussing and thinking about conditional statements. We're going to extend our understanding to include a few of these other options: biconditional statements, contrapositives, inverses, etc. So we're going to put that to work right now. It's helpful to remember that a conditional statement is in this format: if hypothesis, then conclusion; if P, then Q. The converse of a conditional statement is when we switch the hypothesis and the conclusion. If the conclusion, then the hypothesis; if Q, then P. But there are some other ways in which we can think about notating our thoughts. For example, the tilde before the P or the tilde before the Q just negates that statement. So the negation of the hypothesis would mean not that thing. The negation of the conclusion would be then it's not that thing, and that's not this result. So for example, well, actually, let's continue talking about this, and I'll do an example with like when I wear sunglasses or something. So an inverse is when you negate the hypothesis. If not hypothesis, then not conclusion. And the contrapositive is basically the converse of the inverse. You're switching those. You're saying if not conclusion, then not hypothesis. So let's think about it like this, for example. Conditional statement, if it is sunny outside, then I wear my sunglasses. Flip that around for the converse. If I wear my sunglasses, then it's sunny outside. The inverse would be, if it's not sunny outside, then I'm not wearing my sunglasses. And then finally, the contrapositive, if I'm not wearing my sunglasses, then it is not sunny outside. That should give you a good feel for how these statements work. So new vocabulary is inverse and contrapositive. If you don't remember that you're negating that statement, then that's fine. But the big deal here is we know conditional, converse, inverse, and contrapositive. Here's a quick example. If two numbers are both even, then their sum is even. And this is a true statement. The inverse would be saying if two whole numbers are not both even, then their sum is not even. And we can test that by trying to provide a counterexample. A counterexample, if two whole numbers are not both even and their sum is not even, well, here's a simple situation where 3 plus 5, both whole numbers, both not even, but their sum is even. This is called a counterexample. Not just saying it's not true, pick any pair of odd numbers, but actually taking those odd whole numbers and giving a specific counterexample. A contrapositive is when you're saying if not conclusion, then not hypothesis. So again, identifying hypothesis, conclusion, flipping them, and negating both of them. If the sum of two whole numbers is not even, then the numbers are both not even. This indeed is true. There's no counterexample that exists that will show that this statement, that this contrapositive is false. All right? So conditional, flip the hypothesis and conclusion to get the converse. Negate the hypothesis and the conclusion to get the inverse. Negate both and swap them to get the contrapositive. All right? Biconditional statements. So now this is the first vocabulary term on the list, but it's one of the last ones that we're getting to. If a conditional and the converse are both true, we can join hypothesis and conclusion into a brand new statement called a biconditional. All right? And the way that this works is we will say hypothesis if and only if conclusion. And we will use the notation with P and Q and a double arrow to show that we are going both forwards and backwards, that it's reading both directions. You can state it as hypothesis if and only if conclusion, or conclusion if and only if hypothesis. Both are acceptable as long as it reads well, as long as it's grammatically correct, right? We want to obviously do a good job with our writing. And so again, it's the P double arrow Q showing that this reads both ways. Here's our truth table. If the hypothesis is true and the conclusion is true, then our biconditional will be true. If one of them is false, either the hypothesis or the conclusion, then the biconditional will be false. If the hypothesis and the conclusion are both false, then it doesn't matter. We're going to say that biconditional is true. I know that last one feels backwards. It's kind of like two wrongs make a right, or two negatives make a positive. You can kind of think of it that way when we are reading with our biconditional statements, our forwards and backwards. All right? So let's work on writing biconditional statements. In order to do that, we're going to have to think about the conditional. We're going to have to write the converse and then think whether or not our converse is also true. So, and if they're both true, then we can write our biconditional statement. So here's an example. If x equals 5, then x plus 15 equals 20. All right? And this is a true statement. If x is 5, then 5 plus 15 is going to equal 20. That's a true statement. If x were something different, then maybe that value plus 15, would not equal 20. So the truth value of this statement is true. It works. All right? True, yay. The converse is when we flip that statement around. All right? If this is hypothesis and this is conclusion, we're going to swap them for our converse. If x plus 15 equals 20, if I gave you that equation in your Algebra 1 class, you'd say, oh, I would subtract 15 from both sides, and I would say if x plus 15 equals 20, then x is equal to 5. All right, so this is also true. Yay. If it's true, and the original conditional is true, then we can write a biconditional, which would be in the form hypothesis, if and only if, conclusion. All right, meaning we would say x plus 5, I'm sorry, not x plus 5, x equals 5 if and only if x plus 15 is equal to 20. Now again, if you flip that statement around and you say x plus 15 equals 20 if and only if x equals 5, that is also correct, all right? Two right answers for the same question. Here we are taking an if-then statement, we're flipping it to write the converse, we're checking the truth values for both statements, and then rewriting a new conditional called a biconditional statement. Hypothesis, if and only if, conclusion. Do this one. If 3 points are collinear, then they lie on the same line. All right? Thinking through this, we're going to do the same exact thing. I want you to do this one on your own. I will say that the conditional is true, and I will say that the converse is also true, so you can write the biconditional here, just in case that is an issue. Pause the video and do that so we can check that. Make sure that you have this part 2 done. Example 6. And by the way, I'm picking up on the example numbers where we left off last time, so that's why these examples got to be high numbers here, because we already did 4 examples on the previous lesson. Write the conditional statements that form the biconditional. Basically what we're going to do is, given a biconditional statement, let's separate it as if hypothesis then conclusion, and the converse, if conclusion then hypothesis, when we are given the biconditional hypothesis if and only if conclusion. All right? And so what this allows us to do is say hypothesis, if and only if conclusion. Let's go ahead and write out these statements as 2 conditionals. If this is my hypothesis, and then this part is the conclusion, all right, that's our Q, that's our conclusion, this is our hypothesis, then we can write our 2 conditional statements. The first I'm going to do if hypothesis, then conclusion. The second I'll say if conclusion, then hypothesis. Again, paying attention to keep my subject, my noun, not my pronoun form, but my subject in the beginning of our sentence. If a number is divisible by 3, then the sum of its digits is also divisible by 3. All right, this is true. This is a neat trick if you're ever testing a large number and you're like, ooh, what does this number divide by? Well, you can check 3's if the sum of the numbers added up to 3. All right? If the sum of a number's digits is divisible by 3, then the number, or it, is divisible by 3. What we did here is we took a sentence that was written as a biconditional and we separated it as the combination of 2 separate conditional statements, a conditional and a converse. Now it doesn't matter which one you list first and which one you list second, as long as you have both sentences included in your work. All right? Again, structuring those sentences can be a task to make sure that you are thinking and writing grammatically appropriate statements. All right, good definitions. This is a little bit of an add-on for me, just to make sure that we have a good understanding of what makes a good definition versus a bad definition. And this is helpful for us as we define new terms throughout the length of this course, throughout our time together. And we will reference this often throughout the school year as we define new terms. A good definition is something that is very precise so that we can't confuse it with something else. It is using clearly defined terms so that we can understand what we're defining. It's like there's no more terrible a feeling than when you read the definition of a word and then you have to read the definitions of the words that define the word. Like, that's just annoying. And so we want to use clearly defined terms. We want it to be intelligible. We want it to be precise. And we want it to be reversible. Now, reversible is kind of an awkward concept, but we're going to couch it in terms of what we're discussing here, which is reversible means that our definition can be written as a biconditional, so that we're not going to confuse thoughts or ideas. Now, what I mean by that is there are lines that do not intersect that are not parallel. All right, that's a thing. There are these a pair of lines that are called skew lines, and they're in 3 dimensions, not 2 dimensions like we usually have on graph paper. But if I have 2 lines that are in 3-dimensional space, this one going across, this one going up and down, these lines never touch, right? But they're not parallel, right? They don't have the same slope, they're not in the same plane. And so we don't want to say that parallel lines are lines that don't intersect, because that's not a good enough definition for parallel lines, all right? And so we want to make sure that we have good definitions that don't get confused with other concepts or ideas, all right? So here, a triangle is a polygon with exactly 3 sides, all right? Is this a statement that we can write as a conditional, like we did with acute angles in the last lesson? Can we flip it, and will they both be true? If so, we can write a biconditional statement. If a polygon is a triangle, then it has exactly 3 sides. Not just 3 sides, exactly 3 sides. This marker's fading, so I'm going to set this one down. The converse, if a polygon has exactly 3 sides, then it is a triangle. All right? Now, both of those statements are true. All right? I don't know of any other polygons that have 3 sides that are not triangles, right? And I don't know of any triangles that don't have exactly 3 sides. So we don't have any counterexample that can render either of these statements false. So these statements are true. A biconditional would be to take this hypothesis if and only if that conclusion, or this hypothesis if and only if that conclusion. All right? So a polygon is a triangle. Should use a capital letter at the start of a sentence. A polygon is a triangle if and only if it has exactly 3 sides. All right? We have just taken a statement, we've written it as a conditional statement, we've written the converse of that conditional statement, shown that both are true, and therefore we have a good definition of a triangle. It's reversible. It's reversible. All right? Now here's a situation where we have a true statement that is not a good definition. All right? A square is a 4-sided figure with at least 1 right angle. This is a true statement. That is a very true statement. It's not a good definition. I want for you to try to write a conditional, a converse, and then to assess if your conditional or your converse is either true or false. If it's false, if either the conditional or the converse is false, you cannot write the biconditional. You're going to write the phrase not reversible here, all right? But I want you to do these parts, and then I want you to tell me at the end here that it's not reversible on your notes, on your paper. Pause the video if you need to. When you're done, play again. To show that a definition is not a good definition, instead of going through that whole process of writing out conditional, converse, are they true, can I write the biconditional, or is it not reversible? Instead of doing that, you can simply provide a counterexample to the situation to say, this is not a good definition, all right? So on the last one, where you had the square that was that has at least one right angle, you could draw a rectangle, and you can say, well, this is a rectangle and it has a right angle, but it is not a square. It has multiple right angles or whatever else, all right? But it's not a square. All the sides aren't congruent. Those kinds of comments would then show you that you've provided, or show your reader that you've provided a counterexample that says that your definition is not very precise, all right? It's not reversible. And so here is an example here. Is this a good definition? And you're going to explain. So an apple is a fruit that contains seeds. This is a true statement, but is it a good definition of an apple? All right? Or is it a good definition of a fruit? Let's think about situations where you could provide a counterexample to this situation to maybe name something else that is a fruit that contains seeds. All right? And in that way, you are providing a counterexample. So for us, I would say this is not a good definition of apple because an orange also has seeds. All right? And you could probably come up with any other number of counterexamples to show that this is not a good definition for what an apple is. All right? And so, again, we want to think about whether or not we have quality definitions when we're trying to learn new terms. All right, so in summary, and I don't know how well you'll be able to read this on the camera there, but this is a summary of conditionals. If P, then Q. Converse, if Q, then P. Inverse, if not P, then not Q. Contrapositive, if not Q, then not P. And the biconditional, P, if and only if Q. Hypothesis, if and only if conclusion. All right, so that concludes lesson 5. Hopefully you're keen on all this vocabulary. Hopefully you can write conditional statements and determine whether or not those statements are true.